Good morning, evening, afternoon, everyone. Thank you for joining us. We still have quite a few more people pouring into the room, so we'll just wait a couple of minutes until everybody's settled, and then we will begin. Thanks. Okay, good afternoon or morning or evening, everyone, depending on where you're calling in from. Looking at the participants list, I recognize some of your names from different locations, so I think we've got quite a good geographical spread. My name is Ben Loveday. I run the Copernicus Marine Training Service on behalf of EUMETSAT, and I'd like to welcome you to our first marine short course of the year. First of a planned 4. This one is going to be focused on ocean color and new tools and approaches for performing ocean color matchups with OLCI. Joining me today will be my colleagues Hayley Evers-King, Noemi Marsico, and Juan Ignacio Gossn, who will all be showcasing different parts of what EUMETSAT bring in terms of marine data to our community, the tools with which new tools we've got available to access this data, and then the central part of the presentation will be delivered by Juan, which will be on the Thomas toolkit, which is going to be focused on performing ocean color matchups themselves and how to use this toolkit. So as I said before, it'll be myself and Hayley at the very start for an introduction. So Hayley will follow me, and then Noemi will give a short overview of the EUMETSAT data store and EUMDAC, and then Juan will focus on Thomas, our new matchup toolkit. At the end of the session, we will have a 20-minute Q&A session. However, this course is, or this webinar rather, to our webinar is the first part of this short course. There will be, after the 20-minute Q&A, the Q&A platform will stay open for 7 days. We will respond to all of your questions for that time. That will be hosted on Slido, and to access that, you need to go to slido.com, and the code you need to enter is EUMSC35. So EUMETSAT short course number 35, EUMSC35. So that Q&A will stay open the entire week. On there, you will also, next to the Q&A, find a feedback survey, which we'd appreciate your input on. So it's a second part of the Slido, and you'll see 2 drop downs there. You can choose from either Q&A or feedback survey. That feedback survey will also stay open for the full 7 days. And after 7 days, we will have a follow-up webinar session on the 5th of April next week at exactly the same time, where you will have the option to ask live any questions you've got about using the toolkit, putting it into practice, methods of data access for the EUMETSAT Marine product catalog, or any broader questions you have, and we will be there to support that session as well. So the idea behind this is we will give you 7 days to work with the toolkit, and if you've got any questions about putting it into operation, then you can ask us live there, or you can ask us on the Q&A throughout the week, and we'll support that as well. So they're the 3 parts. You will see me sporadically throughout this, but I'm actually going to pass over now to my colleague Hayley Evers-King, who will take it from here.
And we're literally going to change over today, changing seats in the room. So hi, everybody. Great to see you. Hopefully some of you, I'm sure we've met before, and some of you maybe have seen me on one of the previous short courses. So if not, though, hello, I'm Hayley. I'm our marine applications expert in the user services division here at EUMETSAT. For those of you who don't know EUMETSAT, maybe most of you do, but anyway, just in case, we are an international organization. We have 30 member states, and our primary aim is delivering weather data towards weather forecasting and climate services. However, we also operate a number of programs in collaboration and partnership with other agencies and organizations. And in the case of our course today, one of those that you'll be most interested in is the Copernicus program, under which we operate Sentinel-3 and the OLCI mission aboard that satellite. It's not just a European thing, though. We also have strong international collaborations within Europe and beyond with colleagues in the US, Africa, and in many other nations worldwide. So just to give you a bit of an overview of some of the missions that we have here, I won't go into all of these in detail. They're the subject of many of our short courses on their own and in their own right. However, just to show there under the Copernicus program, you can see that we currently operate the Sentinel-3A and 3B satellites, which have ocean color capabilities on them, and we will be involved in continuing this mission through the C and D missions that will be launched in the coming years. and ultimately with the follow-on missions that come in the Sentinel-3 next generation as well. And this is primarily where EUMETSAT's role in ocean color sits, although we're also looking at what we can do with regards to ocean color from our geostationary new generation sensors that are flying now and will continue to fly in coming years. So stay tuned for a short course on that maybe in the future. I wanted to say a few words of introduction as to why we're doing a short course on validation, why it's something that's important. I realize many of you will already know this, but I wanted you to hear from us what we think of it and why we are running this today. So this course in particular came out of some feedback we had from some parts of the user community, especially early career scientists who wanted to know more about this process, something they were maybe having to do during their studies or as part of their research, wanted to know more about how validation is done. So this is then part of our advanced training offer. If you have ideas for other topics you'd like to see in these short courses, we'd love to hear them. You can give that feedback in the survey later on. However, we also like to engage more broadly with the community on validation efforts. So this is also there for a course directed at informing the rest of the community who already maybe do validation about what we're doing internally, and you'll hear more about that from Juan later. So why validation? I mean, validation fundamentally allows us to assess the quality and the relevance of the products that we generate, or if you're a downstream user generating your own products, also the relevance and accuracy of those for your own purposes. So it's very, very important for us as satellite operators, but also for anybody who's developing downstream applications of the data. It's always something we try and recommend people to do, is compare what you get from a satellite with what you can measure in situ. And more, this is a community exercise. This is not something we as EUMETSAT can do alone, nor should we. It's intrinsic kind of to the process of validation to have lots and lots of data. And in the case of ocean color, from lots and lots of different water types. This is not something even with all the money and ships in the world that we could do. So it's something that we get engaged with the wider community to do. And this kind of community approach over years has developed around things like protocols and practices. And these sorts of things need input from the community out there. So yourselves and the long legacy of people who've been validating satellite data. And as a result of that, there's many different community activities out there that support these initiatives. So just to give a bit of a shout out to that, if you're new to the world of validation, you'll probably want to check out what's going on through the IOCCG, so the International Ocean Color Coordinating Group has been a center point for leading some of these activities around practices and protocols. You can contribute data to many databases, including ours, and Juan will talk a bit more about those later on. And you can also take part in validation team activities. So we have a Sentinel-3 validation team. I'm sure some of you listening are part of it already, but if you're not already, have a look and you can apply to be part of this and share what you've been doing in validation terms with the wider community. And I wanted just to end that section by saying, if you have already contributed to these initiatives, thank you. It's a really well-recognized and important community contribution. I think it allows us all to do what we do and really make the most out of this data. So a big thanks to all of you that are part of this initiative. Before I finish up, just a few resources to highlight during this course and more broadly in your interactions with EUMETSAT. Many of you may have used our help desk. This can be contacted by email at ops@eumetsat.int. So any questions you have about our data, products, services, or to get into contact with us, this is a main email stream that you can use. We have a Confluence knowledge base, which provides technical information about our data services and products. It's available at that link here. These are all also on the page where you registered for this course. We have a GitLab, which shares all the code that we've made openly available. And the new toolkit that Juan will present later is on there, as well as the EUMDAC client, so that can also be accessed through other means. We have more detail on our training offer at training.eumetsat.int. Many of you will have been through there to register, I think, for this course, or maybe if you've been on a previous course. But that includes our calendar with all the details of different events and offers that we have in terms of training. I wanted to highlight a few upcoming events. So we'll be at EGU, at the Liège Colloquium, and at the Operational Satellite Oceanography Symposium. So if you've attended this course today and would like to meet us in person, come and say hi. We'll also be running training and other engagement events at these different events there. And in general, yeah, please do feel free to reach out to us. We love to hear from the user community, feedback on our products and services, what you've been doing with them, so that we can promote the excellent work that you're doing. So before we move on, the learning objectives for today's course, these are what was listed on the registration site, if you had a look. So from this today, we hope that you'll be able to recall how to access our EUMETSAT data store and identify the different Sentinel-3 OLCI products that are within it. You should be able to use the EUMETSAT data access client, which is known as EUMDAC, to search for and retrieve products via the APIs, the application programming interfaces. You should be able to recall how to acquire and configure the toolkit that Juan is going to present for ocean color matchups. And then optionally, depending on how far you go and if you engage over the next week before our catch-up session, you should be able to implement this matchup kit to perform matchup analyses with OLCI products and to evaluate the utility of this in the context of your own workflows. We put these as optional because we've only got a couple of hours today. We don't think we'll be able to achieve all this today, but if we engage over the next week, we're pretty sure we can help you to achieve this. And I think that's it from me. As Ben said, the Q&A is open on slido.com, and you can use the hash EUMSC35 to ask any questions, and I would encourage you to do that. We'll come to those at the end. Thank you very much. And it's then my pleasure to hand over to Noemi.
Hello, hi everyone. So thank you, Hayley and Ben and Juan, of course, for the training. So I'm really excited to be here. I'm quite fresh, so I'm going to introduce myself a little bit, so you get to know slightly bit about me, and then we are going to go through the services. Okay, I hope you can all see my screen right now. You see it well? Good, perfect. So what we're going to talk about now is going to be the data store services and the EUMETSAT data access clients. So both of them are our services, and they are a great opportunity for us to download data and to get to know also more information about the data themselves. So we'll go through them. First thing, of course, who I am. My name is Noemi. If you don't know me, if you have not seen me in the previous data access trainings, I am an Earth observation data engineer, for Inoflare and on external contractor for EUMETSAT. By education, I'm a hydrologist and hydrogeologist, so I did focus on optical remote sensing application to study water quality. I have actually done my master thesis on the evaluation of suspended particulate matter and chlorophyll A through OLCI and MODIS sensors. And talking about validation as well, I have worked with a little bit with validation where I was studying the Baltic Sea, and I got the opportunity to go on the research vessel and take samples and compare them with my data. So what I'm going to touch upon today is the data store, the first point we're going to talk about, and we're going to learn a little bit how to download the data from the data store, a little bit of theory, and also some demonstration about it. And then later we are going to pass to EUMDAC. So it's a data access client that is also used for exploring and downloading collections. So also for that, we are going through some theory and some demonstration. So first thing of all, the data store, what it is, what are we talking about? If you have never heard about the data store. So the data store is the single point of access for EUMETSAT data. And this means it contains most of the EUMETSAT data. And just for reference, we have a catalog that goes back to 1981. So it's a lot of data, and we include data from METEOSAT, first and second generation, METEOP, first and second generation as well. And we are incrementally adding a Copernicus mission, so Sentinel-3 and Sentinel-6, which are the topics of this training. The best part of the data store is that the data, you can ask them, they are on demand. So this means that you don't have to place orders anymore. What you would do with the data center, if you have used it before, where you have to place the order and wait for the email to receive the okay to the download of the data. But now you can have your data exactly when you finish the process. So this is a really great opportunity. So I will show you a little bit. Again, I will now share again my screen. I will stop sharing and start sharing another section of my screen, okay, which is just the normal browser, okay? I'm on Google Chrome, and I'm going to show you a little bit how to access the data store and also to find a bit of information about it. So first of all, we are going to go on the EUMETSAT sorry, EUMETSAT website, the normal classic website. And how do we access from here to the data store? So we can just simply go on satellites. Here you have a data user support and how to access our data. So you go directly in how to access your data. We are going to go scroll down a little bit. Here you have some of our services that the data store exactly included. A little bit down, we have the EUMETCAT, and these are our knowledge bases. I will talk about them later because it's way more correlated to what I'm going to talk about later, but just remember they are here. The knowledge base is what you get a lot of information about all the processing and all the technicalities that you need for the data store. So now we go on the data store. Simply here we have another page, a little bit of overview of the data store. This is Ben's video that is really helpful if you need it. And we can go directly here. Here we have the Earth observation portal or directly via the direct link. So this is, you can just simply click on the link, but we're going to do the bit far longer version just so in case you get lost. And here you have the Earth observation portal, and you can simply enter the EUMETSAT data store. Now we are here in the catalog, so you have different ways to search for the collections that you need. So you can either scroll down like you would do with Facebook, or you can search for the collection that you're looking for, or perform an advanced research. So this is what we're going to do now, performing an advanced research. Here you get to choose your filters. You can choose a platform. For example, now we choose Sentinel-3. We are choosing optical. You can choose the sensors, OLCI, the type of access, and a lot of different filters that you can add here. In every collection, really important, you have a navigation, the navigator for the collection. So you get to know by clicking learn more, you get to know a little bit more about the collection. So you have the description, the temporal extent, the way to access it by distribution of by format. Just so you know, every format that we have for Sentinel are Sentinel safe. And then you can get some resources, contacts, and simple technical details and additional information. Here in additional information, you also have the collection ID, which is going to be quite important later on as well, but just so you know, it's here. So how do we do that? We can either just click on access data as you have seen before, or click download. It really doesn't matter, sorry. But we're going to do with access data. With access data, you get a new window. It's really comfortable. It's really self-explanatory. You get to choose your time range. You get to choose, for example, how to sort them if you want to sensing time or ingestion time, the filters, additional filters, so Sentinel-A, Sentinel-B, 3A and 3B, and you can also choose your area of interest. This is really interesting because we have different ways to choose our area of interest. You can either select it here, as you see here in the AOI, you can make a square or a normal rectangle. You can also decide to do a polygon, to have a polygon, but you can also choose by pixels. So it really depends what you find more comfortable. I'm going to just take the Mediterranean Sea and just do this, okay? I will choose the date. So here you have the availability. So you have from 2016 to 2019. This is October. So this should be quite okay for us. So we can show the results now. Here now you have a list of results, and you can see also the image you have by just clicking on it. You see that here it moves. So you can choose a little bit the one you want the most. So we can choose, for example, to use this one. This is South Italy. This is my place. So I'll go for this one. After you have selected your collection, you can just simply add it to the cart. You can download here directly, or you can add it to the cart, or you can also have access to the EUMEDAC download command, which we'll go back again later. So we can just add them in the cart. We can add more collection depending on what you're looking for. So after we have the cart, we can just simply go and check it here. Here you have the API accesses, and that you can open directly. And here you have the cart. So this is the user interface. So we're staying on the cart. Here we can just simply choose one of the collections that we are interested into, and then just simply download here. And our data will be download it. Really simply, it's really easy to understand, and it's really easy to follow for anything. There is a lot of information, and I find it quite comfortable, at least for me. If you're not really comfortable with more like scripting languages, and you're more comfortable with the user interface, then you can simply use the data store user interface, and this is simple and how it works. Okay, so now I'm going to go back to my slides so we can talk a little bit about the EUMDAC. So here you see my slides again, I guess. Yeah, okay, good. So regarding instead the data access client, we have in short we call it the EUMDAC. Okay, and but what is EUMDAC? First of all, EUMDAC is a simplified Python library that is used to access our services programmatically. We have a command line interface that looks exactly like the one you're seeing right now, and we have different ways to download, to search for collections, and download the products that we are looking for. Basically, what EUMDAC is a piece of software that is built on top of our services. This means that you don't have access to any more data that is not related to our services. It's not that you can access EUMDAC and you will have more data than the data store. No, this is not the case, but you won't have even less. So you will just have the same data. It's just much simpler for people that are much more comfortable with using Python scripts or scripts generally, and they want to use, for example, their terminal. So we do have a command line interface, but we can also install our EUMDAC on our own environment, so that works perfectly as well. Now I am going to again share my screen. I'm sorry for all this shifting of places that we have to look at, but okay, sorry, here it is. Okay, so we are back on our Google Chrome. So we go back to our website. Okay, so we are going again on EUMETSAT, normal website. You can access our data here. You just can go down here and here. Now it's the moment when we talk about the knowledge bases and we get to actually open the Confluence pages. So here, as I was mentioning, you find all the information also for the user interface, as I was showing before. You can see here simply data store, for example. You get to know a little bit more about everything, and you can find a way to access data and the data stores. And then I will also shortly mention other services. But here what we're looking for is EUMDAC. So EUMETSAT data access client. And this is this one, the last one. You can see it here. EUMETSAT data access client. Here in Confluence, we have this really comfortable outlook of what is happening and how we can look for products. You can see here we have discovering collection. We can search for products and we can download products. We are not able to customize products yet, but it is on the way, and I will shortly also talk about this. So you have now different ways to access our data by command line interface. And first thing of all, you will need to install EUMDAC. This is the first step we need to do. So we have different as well ways to install EUMDAC. The first one is the command line interface binary. So this works for the people that cannot maybe install anything on their computer. Maybe you're working for a company that's not allowing you to install whatever you want, or whichever the reason is, you can just simply install our command line interface binary, depending, of course, on the machine that you're using, and you will not require any installation. Otherwise, you will need to install the EUMDAC. You can install it from the source, so from Git. You can install with pip or Anaconda. So it's really quite self-explanatory. Here you find a lot of information about how to install EUMDAC. A really interesting part of the Confluence page is also that we do have the possibility to look at the commands that we can use. So if you're deciding to use our command line interface, you can simply access the command line user guide, and you will have all the list of commands that you can use to access our data. And the best part is that this EUMDAC allows you to use the APIs in a much easier way. So if you're not fully confident or comfortable using APIs, then this is a really interesting way of learning and of applying what we have worked on for quite some time. So we also have some examples for the Python library. Instead, if you don't want to use the command line interface, then you can use our Python. You can use it on your Python library, on your Python environment. Sorry, and here we have quite a good examples that how you can use it. Again, it's always in the same page, so you're sure you're not going to lose anything. Here we have one of the great assets that we have, one of the great Jupyter notebooks that we have is the Sentinel-3 data store access. So this is exactly focused on Sentinel-3. And now I am going to show you how this notebook works. Okay, I will have to again divide my screen to another section. Here it is. Okay. Can you see my Jupyter notebook? Yes, I guess so. I imagine so. Okay, I see Juan doing this. Okay, thank you. Okay, so this is our Jupyter notebook about Sentinel-3. So you can have access to our Jupyter notebooks. They can cut out a lot of time, and they really allow you to explore the collections that we have in every way. So this is a really good way to learn. How to look for collections and how to find collections and everything and download then your data, which is exactly what you want to do in the end of the days. So now we can go this is just a simple outline of what is this Jupyter notebook. Now we're starting importing our libraries. We're importing just libraries like Datetime or JSON, and we're also importing EUMDAC here. We are also creating a folder here to allow you to download, and when you have your products downloaded, you will have directly your folder in the same place where you have run the notebook. So you will have your downloads already prepared there in your folder called products. In this case, you're always welcome to change it. Here we have just some like the video and some more information about it. But now we arrive to a really important part, that is your consumer key and your consumer secret. So for accessing the data, we are going to create a token for you, so you are going to be able to access. And for every option that you have, in this case, we have two options. You can see here, option number one, that is asks you for consumer key and for consumer secret. And also we have an option two. This is usually the one I use, and it's also asking consumer key and consumer key and consumer secret. But how do you find this information? This is really important because without this information, you will not be able to access the data. So let me show you again once more. Sorry, I'll have to change again. Okay, so now we were on the EUMETSAT data store. Okay, so from the EU portal, you can enter the data store at any time. So here you can find your data. Just simply, let's go back to the catalog. Just simply on your icon, on your normal login icon, and you can find your profile, and also you find your profile, your API keys. This is exactly where you are going to get your consumer key and consumer secret. You can simply just copy it. There's a simple button here where to copy it, and then you just paste it in your Jupyter notebook. I have already done this. Here, you're not going to be able to see it because if not, you just see my credentials. So I've hidden this part, but you can just simply modify this and just run. In this case, I just showed it to you, sorry. And this part is when then we are starting to create an object for the data store. This is just some exceptions. You can find also much more information about the EUMDAC errors in here in this link. You will have a page on Confluence where you can get a lot of information about the errors, what the error could be due to. So you will get to know how to solve your problems really in a really simple way. So right now we are now, for example, filtering for the collection. So do you remember when I was saying that there was a collection ID? You can find this collection ID on the data store user interface, or you can simply by using the command line interface that I was showing you before, the discovering collection, then you can get to know all the IDs that you might need. So in this case, we're just using this ID and we are creating the collection, the object, and we are just passing this. So we are just, sorry, I don't know what is happening now. Okay, let's ignore that. But then we are going to be able to put, for example, filter the time. This is something that is really important to do generally because we want to know at which time we want to collect the information from a certain amount of time, from a certain date. So really important for you to remember that we do have two different types of dates. One is the publishing time and one is the sensing time. The sensing time is the time that the actual satellite is taking the information, while the publishing time is simply the time that we have made those information available. So here it really depends on the type of on the type of time that you want to set. Here you have, for example, the year, the month, the date, and the hour. So this is 1600 hour and minutes. And after this, that is also after you set the time and date, you might also want to set the space and time. So for this, we have again we can create polygons. So if what I was showing you before in the data in the user interface, you can do it directly here by creating your polygon. Any well-known polygon, it's accepted, but it's going to need more testing and everything. But you can just simply use a polygon, create your own polygon, put in your coordinates and everything, and you will have it done. Okay. So after this, then we are arriving to the point that you can finally download your data. Everything is really well explained in this Jupyter notebook, so you will just see how it works just by running each step and each cell. And here we arrive to downloading the entire product that you need. So here you're just going to have an object selected product, and you will put you will end up having your product in this object, and then it will be downloaded. You can also download by components. So for example, if you only want to download, in this case, is the latest product in a collection, you can also do that. But you can also download, for example, just one band if you are interested. And then just run the code, and you will end up having your data right here in your products folder. Something else I wanted to share with you is that right now, what I was mentioning before, right now we do not have the possibility to customize our data, our Sentinel-3 data yet, but we are working on it. And hopefully the data tailor, there is another service. I will also actually show you in a little second how Okay, so the data tailor, we are working on making the customization of products, so to allow you to also change the format, for example, or for example, doing aggregating, or any other process that you need to do for your customization. You're going to be able to do it, but right now it's not deployed yet, so we are scheduling a training. So I would strongly advise you to check out on our Moodle page. All the links are also in our material, and see when we have this training coming up. So you will actually get to learn a lot more about what we are developing. So these are the ways that are the most important ones that we have been working on now for Sentinel-3. And yes, I think I will stop sharing my screen. And yes.
Is it me now?
Yes, sorry.
Thank you, Noemi. Thank you.
No problem. Yes, I'll pass the word to Juan.
Okay, thank you very much. Just a second. So I hope you can see the presentation now. Okay, so good afternoon, morning, everyone. So I will now go more into detail into this toolkit that already Ben was mentioning. It will use EUMETSAT as Noemi was presenting. So it's good that Noemi introduced all this subject. Just some of you are part of this Sentinel-3 validation team that Hayley already mentioned, and I already introduced this toolkit in the previous version. But we were just sharing it in this non-official GitHub repository. It's now official, and it's now much more enhanced with respect to that status. So Thomas, this is a toolkit to generate matchups of ocean color products with Sentinel-3 OLCI. Okay, this is a tour of what I'm going to talk about today. So I will talk about what's Thomas, the scope, the usage, some background on these matchups and all the processes that are done within the workflow. Some prerequisites to be able to run this code, getting the code, then setting the Conda environment. Then I will give a demo on how to do these 2 steps. And then I will talk about the inputs, configuration, and how to run the code and a demo. And finally, I will just do a mini tour around what's already there in the repository. So please interrupt me at any time. And I understand that this presentation will be available in the future. So I already defined Thomas, but just to mention some detail here. When I mean in situ data, it has to be in a specific format that Thomas can understand. We chose this the CBAS format, or OCDB. So OCDB is the European counterpart. CBAS is from the US, but it's the same format. These are 2 databases which are interoperable. The format is simply a CSV file. I will show you examples, and there are examples already stored in the repository for you to see. And there are also some converters which are already available from some in situ data that the tool will just download it and convert it to CBAS format. But I'm not going to go into so much detail today. And also just that for them, so it's designed for Sentinel-3 OLCI, the standard products that Noemi was mentioning, but the tool, I already tested and worked with it with data coming from the NASA standard products processed with L2 Gen. Okay, and the idea is that it's designed in a way that may be new data with different formats, as far as NetCDF4, or for example, combinations of NetCDF4, or let's say this kind of things. The tool has this configuration to add new types of satellite products. So after running Thomas, you will get in situ data, let's say, transform to match satellite. I mean, transform spectrally. For example, if your in situ data are hyperspectral, so many bands, and then your satellite is multispectral, so specific channel, it would apply a spectral convolution. It will apply band shifting, so that in case we have, for example, multispectral in situ, multispectral satellite, but the bands are not exactly the same, so the response functions are different, so it will apply some band shifting, and it will be this bidirectional reflectance distribution function. So maybe this is a very detailed ocean color subject, but I will just briefly present about this. But this is about the directional correction of our data. Okay, then satellite data. So this is exactly matching what Noemi was saying. This is embedded into Thomas in a way that if you're using Thomas, you don't need to care about whether data is reprocessed or operational and about the collection, let's say, IDs. These are all, let's say, compiled into Thomas. So if you just say, I need the current collection, Thomas will go. And I need full resolution, Thomas will say, okay, the IDs, the EUMETSAT data store IDs are this and this and that. So this is, of course, this is only set for OLCI, okay? Okay, so level 1B and level 2 are supported. And so top of atmosphere radiance, water reflectance. And then it will do extractions. So from this satellite data, the full image, or it will just choose the window that matches your input latitude, longitude. It will be always point latitude, longitude in the case of Thomas. Because we are thinking about in situ point measurements. And okay, and you will choose some size according to what you consider or which matchup protocol you are using. And over the extractions, you will compute statistics according to this protocol, and then you will the two will just sort of merge the in situ transformed in situ with the satellite data into this matchup database, which is the final product, and this will be indexed according to matchup ID pair, so satellite and in situ, and you can perform some temporal interpolation, and it will do statistical matchup statistics on the matchups following the protocol. I will go into detail now of this. So the outputs are netcdf4 files. So we have satellite data as the ones, the raw, let's say the imagery that EUMETSAT data store provides, the mini files, these extractions, the compiled mini files, the in situ transformed data, and the matchup file. CSV summarizing the netcdf content in case you are not so familiar with netcdf, although the netcdf will contain much more detailed information. And PNGs, of course, it's output plots, as the ones that I'm showing here, some spectra in situ, satellite, the difference between satellite and in situ, and then the scatter plots, and for example, metrics here, it's median, percentage difference, all of these metrics will be plotted automatically. I will go into detail then in the next slides. So these are 5 steps. I'm going to go into detail because Thomas is divided into these 5 steps, which can be executed sequentially or independently. If maybe the previous steps you already have your imagery stored in your local system, so you won't go through EUMETSAT data store, whatever. So the first step, as I was saying, is the in situ one. So you need to input the CBAS or OCDB, it's a CBAS input file. And I already mentioned this, as this will make these transformations, spectral matching, DRDF, so directional function correction, convolution, and then this will store in the standard IDB. So repeating is good in case I'm going too fast. And then this optionally you can ask Thomas to query the ECMWF. This is this European Center for Medium Range Weather Forecasts. This is reanalysis data sets that contain ancillary information that may be relevant for your processing. This is, let's say, optional, and you will need some API key. I will show you in the end later how to do this. Okay, the next step. So you will, if you provide your in situ, this will have your lat long of your in situ, your time of acquisition, and you will set a time tolerance, let's say 1 hour around in situ. So then Thomas will just download the data that correspond to your in situ lat long and time range. Either if you want level 1B or level 2. For the matchup, you will need level 2, of course. And mini files, so this is the next step, the extractions that I was saying. So it will, if for example, for OLCI, we have the different products in different netcdfs, it will like stack all of them and slice horizontally to centered in your in situ location. In the case of, for example, the L2 gen out data, it will unnest the netcdf because this is into, you have groups inside the netcdf, so it will just unnest it. This is just comments for those who are familiar with this kind of data. And then the step extraction database, so it will stack all the mini files and it will apply transformations, for example, this bidirectional correction that is not available in EUMETSAT standard products. And then maybe some scale conversion, unit conversion to make compatible for the in situ with in situ data. And it will calculate statistics according to the protocol. And the final step, MDB. So as I was saying, combine both, index according to matchup pairs, time interpolation. So for the moment, the nearest neighbor between in situ and satellite, we may have many in situ to one single satellite. It will choose the nearest one if you request it, and then just provide a matchup statistics. So just graphical summary. So this is a step in situ. So OCDB file, ECMWF file, you will get this IDB file, transform products and bands. EUMETSAT data store, so StepSat data, you will get this list of data matching your in situ in your local system from EUMETSAT using EUMDAC. Then the next step, so from each of the satellite data, you would extract the mini file using this minimization of the distance to center around your lat long. In the next step, you will stack your mini files into a single file containing all the satellite information that you need for your matchup. And in the end, you would just merge your in situ and your satellite into a single file that will contain all the information there. Okay. So this, I won't stop into this, but this is the workflow of Thomas. Maybe it's too much information here, don't worry, but it's just you have the inputs in cyan or blue, whatever, and in green, it's the outputs. And here, so you will need, okay, the in situ submission, ECMWF datasets, optionally, EUMETSAT data store will provide the satellite data, and you will need a configuration file to say, okay, how do you want to run this matchup code? And then these ones are, I put this ones half green, half cyan, because you could either have it as output if you set it in the configuration file, or you can set them manually in case you need more complex kind of searches. We will see 2 examples now. This is again repetition, so I will just skip. Just a bit of background. So according to ChatGPT, our new Google, so what is a matchup in Earth observation? So, okay, ChatGPT answers pretty well this, at least in the shallow answer. As usual, ocean color is listed as among others in the geophysical, in the Earth observation world, and other types of measurements. Of course, we need much more to define, and we have to take much more care, let's say. So we will go into some details of this. Because the idea is not that we just use Thomas without even knowing what we are doing here, because we need to be conscious of what we are exactly doing with the tool. So this is just an example of a matchup scatter plot, satellite versus in situ. In this case, as you see, in situ don't have any error bars. You just see error bars in the satellite component, but okay. So we have to guarantee, before saying our matchup is it's good that we are comparing apples with apples, let's say, that these two magnitudes are comparable. So first of all, we have to make sure you see RRS, or remote sensing reflectance. This is a magnitude that I will define it soon. And we have to make sure that the definition of the satellite product and the definition of the in situ are matching, okay? This is essential. Then we have to take care about the spectral compatibility of these two. So as I was saying, maybe we say 400, but maybe these bands are not exactly spectrally coincident. We have to do maybe some process. And are these two compatible directionally? So maybe the satellite is watching your target from a side, and when you measure in situ, you're watching from another side. So you will need this directional correction. This is, so first, the standard spectral product that we will be compared, this is remote sensing reflectance. We use the same definition as in the Ocean Optics web book. So in case this is some of you don't know, but maybe, but okay, this we are defining here RRS. So this is the ratio of the water leaving radiance and the downdwelling irradiance in air. This is how we define it. Then for band shifting, so for spectral compatibility, we will do this band shifting. In case multispectral, we will do a spectral convolution of LWED, so these two magnitudes, and then divide. And in the case of BRDF, we are going to apply some factor to make this all equivalent as if the sun were in the nadir, so at zenith, and we were staying at nadir. For the moment, Thomas only has one BRDF scheme supported. This is a Morel scheme, so the standard one for oligotrophic waters, but we will have soon other BRDF schemes such as Lee 2011. For the moment, this is the one that we have. Other things that we will have to take care. So are the in situ measurements truly fit, let's say, of high quality so that we can do our validation? We have to take care of this. Then are these satellite and in situ, are they temporally and spatially comparable? So are they looking at the same target at the same time? How can we more or less guarantee this? We know that these are different sources of measurement. So in principle, they are not the same, but we have to sort of try to make them comparable. And then what uncertainty of the value shall I extract from the satellite data? So the first question, the quality of in situ. Thomas does not consider any quality flag to the in situ data. So whatever you put as an in situ data, it will take it as it is and assume it's the best that you have. And so for the moment, there's no quality flag that it will be checking on your CBAS or OCDB input. So, but stay tuned, because we are together with the NASA team, we are developing this quality flag based on in the context of this FRM for SOX, fiducial reference measurement for satellite ocean color study. So in the near future, we will have this quality flag to use over our in situ data. And then, with respect to the other questions, we will have a matchup protocol. So we will say, okay, we will, for example, we'll remove some outliers from our window, satellite window. We will compute some statistic to use as a central value of our window. We will use certain size, and we will follow a matchup protocol to do this. So EUMETSAT has its matchup protocol, and it's available online. So this is already listed in the repository. So you can see the link to the matchup protocol. And it's determining each of these things, but you can use other protocols. So Thomas is sort of flexible so that you can change your protocol, test different window sizes, and so on. So a mini discussion on the EUMETSAT matchup protocol as it is today. So we have our the extraction component. We have our window. Okay, we found our window that is centered in our in situ location. Then we will see if there is any pixel that has any quality flag raised, and these are the flags here listed in this box that we would assume that this pixel is not valid because there's some cloud, there is a a lot of this high glint or whatever. So this will these pixels have to be removed before computing any statistics of the window. So then, okay, we have removed these pixels, and then with this new data set that has, instead of 25 pixels, it has 22, let's say 3 pixels less, we'll check if there is any outlier. So if there is any pixel that has some anomalous value, so and we will detect those outliers based on the, wait, do you see my pointer? I hope yes. Based on this the mean of the data and the standard deviation. So you will detect some outliers, and then you will have your final data set, okay, of valid pixels. And so the EUMETSAT protocol says more than half of the pixels have to be valid for it to be an acceptable matchup, and the window has to be homogeneous. So to check this, you will use the coefficient of variation at this band 560. So this yellowish green, and it has to be greater than 20%. Sorry, less than 20%. If not, you will assume that your extraction is not good. So Thomas will take care of all these steps. Okay. And then not only, we also need some statistics. We need to assess our outputs spectrally, not only in a band per band. We maybe have the scatter plots of a band per band, but maybe it's also good to test our spectral behavior. So Thomas will just output some spectra, the in situ, the satellite, the difference between them, a scatter plot, but with all the bands. And we will have a spectral, this spectral statistics in plotted as outputs. And you will also, you see that there are some spectral statistics, so the spectral angle mapper, the chi-squared, all of these are defined in the matchup protocol. We won't go into this because we don't have time. So we will have these two types of metrics, band by band, in a wavelength per wavelength and in a spectra, and then spectral statistics. That will be one for the whole set. Okay. EUMETSAT's matchup protocol. And again, you can see this is online, but it's also provided in the Git repository of Thomas. And it will give also detail of the window size. So it will be either 3x3 or 5x5, depending on the variability of your waters. If it's really, you can say it's a very homogeneous site, you can choose 5x5 in a way that you have more statistical significance, so more pixels to compute your statistics. And if it's a very highly varying region and very complex waters, maybe you can choose a smaller window of 3x3. This is what EUMETSAT protocol says. The time tolerance is more or less the same. If you can assume that it's very homogeneous in time, very stable waters, you can use a time window of 3 hours. And if it's quite a dynamic situation, your time window tolerance between situ and satellite can be set to 1 hour. Okay. I will do some demonstration of how to run the code. I will use terminal, so the old-fashioned way. But just for those of you who are not used, I will just use very basic commands. I will go very, very quickly through this. So CD in the terminal to change directory. CD with the tilde is to change to your home directory. MKD is make directory, so you will create a new directory. LS, you will list your files in your current directory. ls-a, you will see your hidden files, which is important from our human DAC setting. Then nano is just to see a file. And then conda, which is the way which will we create our environments to be able to run the Python, the scripts. And Git, in case you wish to clone the repository by Git, but then you can also download it manually from the link that I sent you, that is provided here. So, apart from the background knowledge that I was mentioning about the matchup process, to be able to run this, you will need to install Conda, install the latest Anaconda Python distribution. And here I will have to mention that there is some issue when running Thomas in Windows. Maybe this is very common, but because of some problems with the file names and so on. But I think it should be easily solvable. So I hope you have a Mac or Linux at this stage. But it should be very easy to solve. Okay, so you will need conda. So these are the dependencies. So you see here EUMDAC, the one that Noemi was mentioning, but conda will take care of this and install all the dependencies with a single command. I will show you. So to run EUMDAC, you will need the credentials. So I will repeat this that Noemi mentioned. You will need to store them in some place in your home directory. And then in case you are interested in getting ECMWF data and serial data for the in situ component, you will need also credentials for ECMWF, but it's only optional, and store them in this particular file. Okay, I will show you now in a while how to do this. So this, and then to get the code, you can just clone it with Git, or you can just directly download the code from the Git repository with a click. That's it. So I will show you these two slides. Sorry, I'm missing one part. And finally, you will need conda. So you will need to create your environment, and this will be a single. Once you have conda, you just need to type one command and then activate the environment. I will show you this in a while. So just a demo now. So I will leave the presentation and I will show you my terminal. So this is my home my home directory. Just I will also show you if I find it. Here. So first of all, conda, as I was mentioning, this is the Anaconda site. You just type Anaconda in Google and you will get this. And you can follow, okay, you can install it either on Windows, Mac, or Linux. Remember that Thomas is still not working on Windows, but okay, you can just download conda from here. I'm assuming that we already have conda installed. So then to check if conda is properly installed, you can open your Anaconda shell, or in case of Linux, just your terminal, and you just type conda and okay, it's good. Okay, you will see something like this. Okay, just the options for conda. On the contrary, you will get, I don't know what conda is. In that case, you don't have conda installed. Okay, the next is on data store. So this is just a repetition of what Noemi said. It's good to just consolidate our learning. So you will need, so here's the data, the web page for data store. You see all the collections and so on. You will just need to log in here. So you see, I already have a user. In case you don't, you have to create a new user for the Earth observation portal. So you just log in here. And then, blah, 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 it's loading. And then you will need to get your consumer key and consumer secret. So that's what Noemi was mentioning. So here you come and you see API key. So you just press here. Unfortunately, conda doesn't show my keys here. So I just copy my consumer key and consumer secret. And what do I do with this? To make Thomas run, I will need to store this in a specific file. This is so I will just show you this file. So it has to be in your home directory. To know which is your home directory, you can type cd tilde, however you call that symbol. Okay, I'm already in my home directory. Good. And then to list the files, ls, this is the command. We'll see all these files, but I need also the hidden file. So the one that starts with a dot. So this is the reason why I need ls minus a. So I will show you. I will have here is .eumdac. So if this is a folder, that's why it's in blue. So if I go inside this folder, right, so cd eumdac, I have my credentials and I have credentials fake. It's the one that I'm going to show you. But you need to, for Thomas to run, you need to put in credentials, the credentials fake here. I will just open, I will just open this file and I put a consumer key, fake, comma, consumer secret. Okay, and then you just exit and you are ready to run EUMETSAT now that you have your credentials stored there. Okay, next is, in case you are interested in ECMWF data, you just, there are two data sets. The ECMWF has several analysis data sets. We are interested in two types, the meteorological ones, and for example, to get the sea surface temperature, sea surface salinity. I would just compile the ones that I think may be relevant for your matchup process. So this is the climate data set, this is this one, and then is the atmospheric data set, this one, and this has information on aerosol optical thickness, for example. Both of them, you have a URL and an API, and you need to log in and or register. This is very easy once you have that. And for example, I just log in. Okay, I already registered, so this is prompting here. If I type here, okay, sorry. Yeah, if I have type here, if I press here, I will see my keys. I won't show you. But if you press here API, you will get your keys. The same, this is for CDS, so climate, the same for atmospheric data set. You will do the same process, login, blah, blah, blah. This is all detailed in the README of the repository. So then you will need to store this in a file. So you go to your home, so cd tilde to go to your home, and the file is also hidden. So sorry, that's means. And it's called ECMWF API config. This is the true one. The fake one is this one. So I will just show you the fake one, of course. Fake. And you have the CDS and the ADS, and you have your URL and your key. So once you have this file in this format, you are fine if you wish to query ECMW. Okay. Okay, maybe you are not interested in this. And finally, we need to get Thomas. Okay, so we go to the link that was provided, and you will get to see this. Okay, so these are all the files in the repository, and this is a README which has detail of all of this. And then either you git clone, so I will do that. I will do it in the git way. So I will just maybe in another terminal, I will do a directory where I want to store Thomas. It will be called Thomas inside my home, and I will just change directory to there, and I will just have it stored here. So I will just git clone, and this is the URL, and I will put this dot so that it stores everything directly in this directory. So it will take a while because it has some sample files, so they are a bit heavy, but it will take maybe 1 minute or so. So while the git, while Thomas is installing in the git way, I will show you, maybe if you hate git, whatever, and you want to download it in the traditional way, you just go here where it says download, and you just download it in whatever compression format you wish, and then you just have to uncompress and place it correctly wherever you want to put your code. Okay, this concludes the first part of the demonstration, which is a setup. So I will again go to the presentation. I hope I'm on time. If not, just tell me, someone. Okay.
Hi, Juan. It's Ben. Things you're going great. Can I just ask, is it possible for you to zoom in on your terminal a bit to make that part a bit bigger? Because it's a little bit...
sorry. Yes.
No, it's fine. Just it might make things a little easier.
I don't have. I think I can't. I don't know.
No problem.
I'm sorry. Yeah. Maybe. Yeah. I don't know how to do this, but I hope you are using glasses. Okay, going back. So I will just show you some examples of what is needed as input. So the CBAS and all this. Just this is the workflow I showed you a while ago. So we will need a configuration file. So I will give you some examples. You have this in situ submission, in situ file. And I will show you 2 examples. So first of all, what is a CBAS format? So this is an example of a dummy CBAS file. So it has a header. It has a header with this slash beginning header, end header, and you have some how to say this information, global information of your set. So investigator, which is the affiliation, the contact, when it was received, processed. Many of these are just optional. So I will I will show you how to check if the format is correct. And this is important if you have this wavelength option. So it can be either hyperspectral or multispectral in case you're submitting RRS. It could be that you are submitting only to total suspended matter. So your matchup will be doing matchup of this TSM, total suspended matter product, or chlorophyll. So maybe this is a wavelength option. You don't need this because it's non-spectral, let's say. And then your instrument model, manufacturer, some of these are optional. And I will show you now that, okay, I will show you later. So these are some comments, and then the fields and the units. And this is just the table. It comes right after you end your header, following these fields and the units put here. So just description of this format, and you have samples in Thomas, and you have description of this format in the CBAS webpage and in the OCDB webpage, because these are interoperable and they ingest exactly the same kind of files. So the only addition, this is BRDF option, so this bidirectional correction function, this is still not implemented in, so it's there in Thomas, but maybe for CBAS we are under discussion about how to do this. But okay, for Thomas, if you just don't put this, it will assume that your data are not BRDF corrected. Okay, so this is a sample file for CBAS. So there is documentation on how to get your in situ data in the correct format. You can try submitting to OCDB that will guide you in the format in case there is any error. And Thomas contains, as I was saying, some sample files. So I will just go through a first example of how to run Thomas. So suppose I am in the Gironde estuary here in France, and I am this location. I have this in situ instrument measuring continuously in these 5 days, first 5 days of September 2021. And I want to get the Sentinel-3 data that correspond to this specific time and location. So here I want only Sentinel-3A, I don't know why, because I want to make it run faster. And I want only level 2. So level 2, the only thing we need to know is the name of the collection. So then I will show you then which are we have one name for level 2 and one name for level 1. So it will care about reprocess operation. It will take care of that. And I need a full resolution. So 300 meters is a resolution for OLCI. So I want this satellite data, and I want to do extractions, so the mini files, and compile them and do the statistics following my, for example, EUMETSAT protocol. And I want different window sizes because I want to test the homogeneity of the sites. So I want 3x3, 5x5, 7x7. And I want to store everything in this output directory in Gironde. Okay. So the configuration file will look like this. So you have a global section. So where you want the output, okay? The output, you have to give a full path to your output. You have to give a name of your set. So set ID Gironde. And you have to say, remember, you have 5 steps, which steps you plan to run. So sat data, so get the data, make extractions, and make the statistics over the satellite extractions. Then satellite section. So this will take care of what type of satellite you want. So first, where you want to store your data. So a path to your satellite data, it doesn't have to exist. It will create it if it doesn't exist. The source, so EUMETSAT data store, this is the tag that you need to put here. The name of the collection, so this is the same that I put here. And the platform, I just care about Sentinel-3A. We could put commas, Sentinel-3B here, and it will get both. And the resolution, full resolution. And then I will do extractions of 7 by 7 centered in this point for this 5.6, 1.6 west. And I will, the extraction, so the metric, the statistics will be done on 3 by 3, 5 by 5, and 7 by 7 because I want to test all of these. And I'm going to use EUMETSAT protocol, so I use this tag. These are all the tags, the valid tags are listed in the README and so on. So EUMETSAT standard level 2. And what I'm missing here is the latitude and longitude and all that. This has to go in latitude, this file, so lat, long, time, ranges. So you put latitude, longitude, time start, and time stop. This is the easiest way. There are other ways to execute this, but this is the easiest one that I found. And you see time start and time stop. You see that the way in which time is provided here this is the standard ISO compatible way of putting a timestamp. So year, month, day, T, hour, minute, second. So it's the first 5 days of September 2021. This is one example. I will run afterwards in the demo session, and I will use another example. This one with in situ. So in this case, I have my in situ, but I don't care. I don't want to process in situ into the Thomas. I just want to the satellite component to be processed. And then the example 2 will be I have a file of MOBI data. MOBI is an in situ instrument. It's in CBAS format, and this is not corrected for BRDF, for direction of measurement and sun. And I want matchup, so the full workflow. I want a Sentinel-3A OLCI standard full resolution level 2 in the current collection. So everything the same, let's say here, with the same EUMETSAT extraction protocol. And I want a window of 3 by 3. And I have to define a time tolerance. So for example, 1 hour. So this is put into seconds. So 3,600 seconds. I will show you how this will see in the configuration file. I'm not interested in the ECMWF ancillary data, so I don't care about this. And I want to apply a BRDF correction for satellite and in situ. I want to make them directionally compatible, let's say. You may have, you may have several in situ, many measurements in your time window. You will just select the one that is closest to the satellite overpass. And then you want to store the satellite there, and you want all of the outputs to be stored in this, let's say, directory. So this is how your configuration file has to look like. So your output, your set ID, all the workflow, you have all the 5 steps, and then the in situ input. So where is your CBAS file? I will show you now how the CBAS looks like. Your CBAS file stored. So this is in situ section because we are running in situ. The time tolerance between satellite and in situ. So you know how to search with EUMDAC. So the tolerance window is 1 hour, so it's 3,600 seconds. I don't care about ancillary data from ECMWF, so I put here false. And I want Morel, the only one that is currently implemented in Thomas, it's Morel 2002. So the tag is M02. And then for the satellite data, I want data to be stored in this place, and I'm here repeating the same as before: the source, so EUMETSAT data store, the collection, the platform, the resolution, and the BRDF. So I want also to apply BRDF more L02. I put here 3x3, but here it says 5. So there's some typo here. But okay, let's assume here it says 5x5. So I want a mini file window size of 5, and the extraction database will be of win size 5. You have to choose a number here that is smaller or equal to this other, because if not, you can't do the extraction. Okay, so the mini file win size has to be the biggest number, or okay. And then the protocol, EUMETSAT standard protocol, and then the MDB section, the matchup section, the time interpolation. So this is a tag. In situ will be interpreted as satellite, the nearest neighbor. This is the name of the tag. It's described in the README. I will want to produce statistics and plots, and I will use the statistics protocol, so from EUMETSAT. Okay, so median, average, deviation, and all of this, which are defined in the EUMETSAT protocol. We don't need to define latitude, longitude, and time, because these are already included in the in situ submission. So this file will be created automatically. Okay. Okay, these are the two examples. Okay, so I have the configuration file. I have all I need in both examples to run the code. Okay, I have my credentials from EUMETSAT stored in the correct place. I have my ECMWF credentials if I want to stored. I have my Thomas code cloned. I have my Thomas Conda environment set up and activated. And I have all the requirement inputs in place. So configuration file, the in situ file, and so on. So if I have all of this, okay, everything is set, and I have just to run Thomas with this command. So Python, the Python, then you're running the main script, which just summarizes all the steps, and your configuration file -cf and the full path to your configuration file, just to make sure that it finds it. So I will show you a demo of these two examples, and we are getting to the end. So I prepared everything here. I'm now in the first example, so Gironde one. Okay, so I have my inputs here. So this is first of all, I have to activate my Thomas environment. I forgot to demonstrate that. Here to just a second. So I forgot to show you that inside okay, here we have already Thomas cloned already, and all of this is a Thomas repository, all of the scripts, and you have this environment.yml. This is a file that sets your environment. So I will just show you what's inside. You have all the dependencies, the ones that I have listed a while ago, and including EUMDAC. Okay, it has the current version of EUMDAC, which runs much faster than before. I remember presenting this in Sentinel-3VT, and there was someone saying this is very slow. So this is a new EUMDAC version, which is very fast. It's good. Okay. So to create the Conda environment, it's Conda. Sorry, I have my cheat sheet because I'm afraid of making any mistake here. It's Conda. Just a second. Conda minus. Yeah, Conda. The file, so it's environment YML. This file will take care of all the dependencies, and you will name it Thomas. Let's say. If you click here, I won't do it because I already have it installed. But you just enter here, and Conda will take care of creating the environment. Okay, I won't do that because I already have it. So I just will activate the environment. So Conda activate Thomas, and it's there. So you see Thomas here. So the environment is correctly activated. Okay, now going back to the Gironde. So I have to activate my Conda in this terminal as well. So I activate it, and just to show you, these are the inputs that I was mentioning in my slide. So the config file, you see all that I was showing before. My home environment is still seen as home Gossn, okay? All of this already detailed here, and the lat long time ranges. So with this was the first 5 days of September 2021, and this is the latitude, the longitude, and the time start and the time end. So you see, you have to respect this format. If not, it will just crash. I always try to put a good error messages. Sometimes there may be some issue, but I try to make them clear so that you know why it crashed and you can correct this. Okay, so it's just what I miss is just to execute the code. So I just put Python. So Thomas, which is under home. So I put just Thomas main, the main script, and I just configure. And I just put input configuration file, which is already here. So I just put config file, and I just click enter. So this will take a bit of a while, but so first it's just importing all the modules and all of that. So it takes some time. If it fails here, this will be terrible. And I hope it doesn't. But it will take some time, and then it will start downloading. So you see it's downloading the data. So it found, for example, this Sentinel-3 product. I think it will find 3 or 4 because I already ran this. So you see step sub data is now executing. Okay, and I will just leave this running, and then I will show you the outputs. And then I will run the other example. So this one is for Mobi. I have created already my Mobi folder here. So I will activate Thomas Conda environment. And I already placed things here. So the inputs are the config file and the OCDB, the Mobi submission. So I will show you the other ones. It's because I don't want to take too long here. So I just already pre-computed all the satellite component. That takes a bit of a while because as I will show you here, I will show you the CBus file. So this is a CBus file, and I decided to put several in situ. So each of this is one station, and here you see the date and the time. You have the latitude and longitude. So the time and longitude ranges will be taken from here with the tolerance that you're given in the configuration file. And then these are 30 stations. So it will take a while to download 30 Sentinel-3 data. So I already did that. So Thomas won't repeat the process if the files are already there. And the configuration file, just to repeat, is the same one that I was showing there. Here I put 5 by 5. I think this is the correct one. You see time tolerance of 1 hour, the in situ input. Okay, the workflow. I will go. So the output path, the set ID, the workflow, the in situ input, the time tolerance, the ancillary, BRDF, and so on. Then the satellite component, which kind of satellite we want. We want Sentinel-3A from the recent collection. We want to get the data from EUMETSAT data store, although it's already stored in my case to make it faster. We want it to be placed here, the platform, the resolution, and BRDF. Then the mini file window size, and then the extraction. So the stacking of all the mini files with the standard protocol and with this window size, which is coincident with the mini file time one. And then the matchup component, where I want interpolating to the nearest neighbor, so the closest in time. I want to produce the plots, and I want to use the protocol statistics as in EUMETSAT standard protocol. So I have everything in place. I will just here, I will just run the code. So Python, again, the same thing. Thomas. Main, so the main scripts, and the configuration file is already here. So it should be running. Okay, it's taking a bit. So this one will run faster because all the satellite component is already there. And you see the step in situ, the first one. Oh, okay. We create the in situ database file. So transform the in situ data. It will, the step satellite data is already, I mean, it's just mentioned here, but it's not executed because the data already exists. The mini files already exist, and this is mentioned here. Then the extractions files are already there, so they are not executed again. And the step MDB, which is the last one, this one is creating the MDB, so merging in situ and extraction, the file, the CSV with the summary, and the plots. So this is already finished. Okay, this is very fast because the satellite data are already there. So I will show you the plots. So for that, okay, you can open your classical. I use Mirage. Okay, you can use whatever you want here. So it's MDB. The plots are inside the MDB directory. And for example, I want all of these plots. So I just you see, so these are just 30 spectra. The colors here are ordered in a way that these are ordered in the 560 band, so that then when you compare with satellites, the colors should be matching. So the violet with the violet and so on. Maybe it is better to just check the consistency of the spectra. Then the difference between them, so satellite minus in situ, you see the statistics, the spectral angle match, mapper, the chi-squared coefficient, and then the scatter plot of all the bands all stuck together. You see these are 10 bands, which are, okay, OLCI has more bands, but MOBI doesn't have the 865 bands, so it's not plotted here. Okay, and then the median deviation, the median absolute deviation, all of these statistics are plotted spectrally. So as you can see, as usual, the 400 band presents higher absolute deviations than going to the red, of course. And these are the percentual deviations. So the absolute one and the non-absolute one. So 10% and so on. And then you have the plots per band as well. Okay, I'm almost done with the demonstration. And I hope that the other one, okay. Okay, here is has downloaded the Sentinel-3A. Maybe here I just clicked something and it has an HTTP error, but yeah, so it's only creating the Sentinel-3A. Maybe I committed some mistake here in the config file, but you have the Sentinel-3A and the mini files. So I will just show you just to check a while. So the config file. Okay. Sorry, I meant to just use Sentinel-3A here. Okay, but in any case, it's fine. So you see the outputs are the satellite data. So I will just list whatever is inside there. You see the satellite data here, which are already unzipped and so on. Then yeah, you have this list of data, but okay, these are just lists which are saying, okay, for this time range, you have this data and so on. You can explore this afterwards. And then the satellite datasets file, this was, oh, sorry. The satellite datasets file, so this contained the detail of, well, here I put Sentinel-3A and B, and details of the platform, the sensor, and all of that was given in the configuration file. Then you have this EUMDAC inventory, so that you know which searches were done for EUMDAC. And the most important is the mini files and the EDB. So just to show you, I think I can show you with my file browser. This is Gironde. Okay, it's a bit slagged now. Just a second. Okay, I don't know why it's not working. I will try to open it again. Just 1 second. So this is because I'm working with the server, so I need to access the server. It's just a second.
I really like the flying penguins anyway. Before
Okay, which one? The
flying penguins that you had.
It's Mobax. I don't know.
The meantime that you figure that out.
Okay, so then this is this first example, and this extraction database. You have the netcdf files. You remember that we asked for 3 by 3 and 5 by 5 and 7 by 7. So I won't go into the netcdf, but it contains very detailed information of all. I will just show you the CSV, which is more shallow information, mostly the basics. It's opening now. And you get global information, so the description of what's inside the EDB, institution, contact, creation time, the protocol, the window size, the spectral data, the spectral products, so RRS, aerosol optical thickness, angstrom, the non-spectral chlorophyll to suspended matter, the power which is given in a single band, the ancillary information, the flags that I excluded to do the extractions, the flags that I exclude per specific product. So for RRS, for chlorophyll, for TSM, we have a special flag, so I just put it separate. Then the outliers. So we use these two rules. So if we are below the mean of the window minus 1.5 standard deviation, or if you are above the mean plus 1.5 standard deviation, we consider this as outliers. The statistics of mean, median, standard deviation, interquartile range, coefficient of variation, quartile coefficient of dispersion, number of pixels, number of pixels flagged, number of pixels that are detected as outliers, and then which magnitude you use as central value of the window. So in the EUMETSAT protocol is median, then you compute the standard deviation, the coefficient of variation, and the macropixel screening. So flag-free fraction has to be less than 50%. This is the way in which is put here. And the coefficient of variation for the RRS has to be greater than 560. Sorry, what did they say? RRS, coefficient of variation of RRS in 560 nanometers have to be less than 20%. And then, okay, all of these details. And then in the end, you get extraction. So for each of the extractions, you get, I will just, sorry, I will just maximize this so that you can see it. Maybe yes, Ben was saying maybe I can view maybe 200. Well, much better, right? And so you have an extraction ID. You don't have to care about this. It's just the ID of each of the extractions, but you have the satellite, each of the satellite name of each of the products, the query latitude, the query longitude, the solar zenith angle of the mean solar zenith angle of the window, the observing zenith angle, and then you have the products themselves. So remote sensing reflectance at all of the bands, the median. Then you have the standard deviation in all the bands. You see that there's one line that doesn't have anything. This is because it failed. So there was, for example, there was a cloudy image. So you don't get anything here. If you want to see what happened, you have to go to the netcdf and you get all the detail. And then the coefficient of variation. And then the aerosol optical thickness in this only band that we retrieve, the median standard deviation coefficient of variation, the angstrom exponent of the aerosols, the chlorophyll, TSM, PAR, and that's all. Okay, I've talked too much, but I think I'm already almost done. Just one thing remaining is to show you how to define your own protocol. So the demo is already done. Here, I will show you. So this is the Thomas repository again. And you will see here is the protocols directory. And these are divided into different processors. For example, there's L2 Gen, so Aqua, Modis, Suomi, and NPP beers. And for our EUMETSAT, we use IPF. Okay, it's the processor we use is called like this. It's typically not very well known, this name, but okay, it's called IPF. Sentinel-3A, and these are many protocols that I've been using to test different matchup processes. The one that we are covering in this example is the standard EUMETSAT protocol. So if you have this, if you set your file here, you just create a new file with your new protocol here, following the same format, you can get your own protocol. So what you have to respect is these three sections. So which flags you are using for screening each of the products. So there are global flags and then specific to each product. How outliers are detected. If you don't want to detect any outliers, you just keep this empty. And here you could just change your statistics, use median, use another coefficient here, and so on. And then the statistics that you want to store, which is your measure of central value of the window, which is a measure of uncertainty or dispersion, and which is a percentual dispersion, the coefficient of variation, standard deviation, and median in this case. And micropixel screening, for example, there are people that they want all the pixels to be valid. So here you would put RRS. So this works in the negative. So if the flag-free fraction is less than 50%, this is a flag. So this is invalid. So for the most stringent people, we would put that if the flag-free fraction is less than 100%, so if there is any one pixel which is flagged, then the macro pixel, so the window, will be flagged and your matchup is not valid. And then the other rule is for homogeneity. So you have the product, then which statistic, you can put any statistic here as far as it's defined here, which band, in case this is a spectral product, and you will flag products we have coefficient of variation of this of RRS and 560 greater than 20%. You can change this if you are a very stringent person or whatever, you can put 10% or whatever. So, okay. I think I'm already done. I covered all of these points today, so I hope you enjoyed it. I hope I wasn't too slow or too fast, and any questions are welcome. Thank you. I will stop sharing so I can see you.
Just sharing me again. There we go. Okay, so thank you very much, Juan, and thank you everybody for staying with us. I note from the number of participants that pretty much you all made it to the end, which is very encouraging and fantastic. And we've got some really good questions actually coming through so far about different uses of Thomas, and some nice comments as well, which is great. So thank you for whoever said the demo was great. I agree. I'm looking forward also to using the Thomas toolkit more extensively. The first question we've got is, how do we tell Thomas that satellite files are already downloaded? Perhaps one for you.
So yeah, I didn't mention this. I always use the EUMETSAT data store as a source, but you can put source local, and then so you can do that, and then Thomas will go to where you stored your files, and it will do a list of these files which are compatible to your query. So for example, you have a directory with Sentinel-3A data, but also Modis, everything mixed. It will only detect the ones that are compatible with your query. So the option local, let's say. Yeah.
Great. So next question. Sorry, I probably missed something. Can Thomas match up with different in situ data formats in case I have one of my own?
Essentially, no. But there are, I already implemented, because of internal usage purposes, some converters. So for example, we use Mobi data a lot, and I did this converter so it will download the data, which are in a whatever format, the Mobi format is, and I'm converting it to OCDB. So it always needs OCDB-like or CBAS-like format. The same for AeroNet. So there is, and you can see in the README, there is a converter for AeroNet data. So you put your AeroNet station, and it will download the station, the data, the quality level. AeroNet has two quality, 1.5, 2, and it will get that station, and it will convert it to a CBus compatible or Thomas compatible in this case a format. So you need to convert it, because if not, it will not understand.
Okay, thanks. The next point was a really one for me, suggesting to add --depth equals 1 to the git clone command to avoid getting old commits. Thank you for whoever noted that, and thank you for that note taken on board for me to tidy up and squash some of our commit history for a load of stuff that you don't need. I will take care of this as well. Next question: Does Thomas regrid the level 2 data sets for matchups and statistical analysis?
Okay, no, so matchup is done at the level 2. So the only thing is that, for example, for our OLCI standard products, some information is given in these type grid points, so not in the full grid. It's only some type points, which is a bit more sparse grid. This is the case for viewing and sun geometry. So in the minifile step, Thomas applies an interpolation to do that, to turn the solar sending angle and everything into the standard grid. But I don't know if you mean exactly, for example, if you want to do matchups over level 3, or in that case, no. So Thomas, it's dealing with level 2 matchups for the moment, let's say.
Okay, the next question: can we only use in situ RS values in Thomas for matchup validation, as opposed to, for example, in situ TSS concentration at a certain site?
Sure. So if you submit only RRS, so Thomas will take care of which are the products that are both in the satellite suit and in the in situ. So, and those that are matching, it will create matchup. So if you just, for example, in your CBA submission, you only put TSM or TSS, however you call it, you will get TSM matchups, because we have TSM both in your in situ and in the satellite. So as far as it's in both, you get the matchup results. And just an additional point on this. So for example, for EUMETSAT matchup protocol, let's say you want to validate chlorophyll. So chlorophyll, the statistics that is recommended is not, for example, the median absolute deviation, but the log 10 transformed one. So so the EUMETSAT protocol takes care of which statistics corresponds to which product. This is following, I think it's paper Seegers et al. 2017. I don't remember now the year. But because this is a normally distributed magnitudes, so we use log normally transformed deviation metrics.
Thanks, Juan. I think the next one down we've already done. In the Thomas workflow, can we skip step number 3 with mini files if we just want the EDB or MDB, or does the EDB step necessarily start from all mini files?
So EDB step starts from mini files because, as I was saying, so the mini files step takes care of stacking all the information to a single net CDF, and it's sort of a first standardization. Like, for example, it will apply the regridding that you will need, and for example, if you want to flag by your sun zenith. So you need, and this flag is in a pixel by pixel basis. So you need the full grid. So this is done in the mini file step. So you need the mini file step, but yeah, you should need it. You should first compute mini files, get them to then compute the rest. Good. I see the next.
Yeah, the next question, I think you hit the nail on the head with your discussion with regards to AeroNet OC, because we have a specific question on where that protocol is inside Thomas.
I can show you. is it fine if I share my screen again?
Oh, yeah, I think it should be.
So if you share screen number 2. So you have this README. So the README is essentially this thing, and then for the you have running the code here, and if you go to the in situ component, in situ, EUMETSAT data store, only processing around here. Let's see. We have a README for in situ component, and by the end of this, you have the 2 converters that are already put there. If you want, you can collaborate and add converters. So for the moment, I only have Mobi. So you need to add an additional Mobi section in your config file. And for error, so just these are the mandatory. So where you wanted to store your raw Mobi data and the time range of interest. For the AeroNet OC, it will download all because it's easier. So it will just download all stations, but then for only this station, AeroNet OC station, Helsinki Lighthouse, it will just compute. It will just do the CBus file. So here's a list of all the AeroNet sites. And yeah, then it's very simple. It's that an additional specific section for the converter. But that's all.
Okay, so I think last question I think we've got is the bottom one here. Question regarding Thomas L2 satellite data. Can the atmospheric correction be from various processes, e.g. Acolyte?
So it's the similar situation as before. So for the moment, there are some implemented. If you want to test with Acolyte, you need to say, Thomas, how to interpret the Acolyte products. So to do that, I will share my screen again. This stop. Oh, sorry. Yeah. So screen 2. So to do that, so this is where the configuration files for each of the processors is stored. So SAT data, mini files, and so on. So these are the ones that are implemented. So for level 1, IPF, so our products, EUMETSAT products. Level 2, L2 Gen, and these are just some aspirational products that I won't cover. But so, for example, Sentinel, the ones that are implemented, you have to just give a configuration file of how the names of the products are given in your netcdf. So I don't recall now how Acolyte stores the outputs in the netcdf. I do recall that it's a single netcdf, you know. So in that, it's for example, you have to give a format. What's a typical name of your Acolyte output, and then these are checks. So for example, it will check that the resolution is a full resolution or the reduced. You don't need to put this. All of this is just don't care about this. In the format, you should put, for example, single netcdf or multiple netcdf, and then where are the latitude and longitude stored? Sorry, I will go to the L2 Gen, which is closer to let's say Acolyte, because it's single netcdf. So it's single netcdf, and you see latitude is stored in this group called navigation data for L2 Gen. So I don't remember. I think that Acolyte just doesn't nest the outputs. It's just a single netcdf group. So you have to take care of this, defining what products are inside the Acolyte suite, and then which bands, and then you have to say, okay, how is it named? Because, well, I don't know. For example, OBPG, they name it RRS 412, for example, and in EUMETSAT we use water reflectance, so which is pi times this. So then I would put a conversion. You will see in the examples. But this is the way. Just you have to set your proper configuration file. Maybe in the future I will put it. But if you want to do it before, you're welcome.
Yeah, and I believe there is one final question. Is there any plan to expand to other satellite sensors like S2, MSI?
It will be the same. You just need to tell Thomas how to interpret the data in the sense that, but yes, this is in my plans. It's just that, yeah, I focused on Sentinel-3, but in the future, yeah, I would need to just set the configuration file as I was showing you for Sentinel-2. So this configuration file is specific on the processor, so it's a standard or whatever, Acolyte, on the level and on the platform and sensor in principle, because depending on platform and sensor, you can have different bands and so on. So in the future.
I would happily add a note on that. If you have a particular request for something or some capability to be added to, we would very much like to hear from you and welcome discussion around collaborating to bring that together. You are freely welcome to make comments, raise issues, fork, collaborate on our toolkit, to reuse it, adapt it, update it as you see fit, and anything you develop that is that we can incorporate into the wider structure, we'll happily entertain discussions on this as well. So if there's something specific you want to do and you have some time to develop it, then please open discussions with us on this. So I think these are all the questions that we've had so far. Thank you all for your engagement. If I can bother you for a couple of minutes of your time, on the Slido, you will also find a feedback form on this and other future EUMETSAT events that you may want to kind of reflect on how this went for you. What did you learn? Did we satisfy your requirements? What do you want to see in the future in terms of training? Then we'd really like to hear your feedback on that to help us design courses in the future. The Q&A platform will stay open for another 7 days so that you have a chance to download the toolkit, work with it, see how it feels, what you can do. And then 1 week from now, we will have another webinar session where you can give us your feedback live on how things went for you. I should say webinar, sorry, this is more a discussion, more two-way. And we will monitor the Q&A through the next 7 days. So we will respond as quickly as we can to any questions you've got whilst you're actually working with the toolkit and or your experiences with the data services and using EUMDAC to download products as well. Otherwise, you can reach us via all of the communication avenues that we shared so far, all of which I think are on our Moodle page. So the page where you registered now has access to all these resources. The recording of this presentation will be uploaded there too, so you can refer back to this. For those that answer questions on Slido, I will go through the recording and then transpose the responses to your questions into the relevant places so that you can see where they were answered as well, so you don't have to go back through the whole recording yourself. Any questions, Juan, Noemi, Hayley, and I will pick them all up and get back to you ASAP. And we hope to see you next week if you've got something to share about using the toolkit. Otherwise, thank you all very, very much for your time, and see you at some other training events, Ocean Color events soon, we hope.
Thank you.